Until this point, we have sidestepped an important question: how to select the number of mixture components that you are going to include in your model. Today, I want to address some of that, and I want to talk about selecting the number of components. Now, knowing what the number of components is important for multiple reasons. If you are in a density estimation problem, remember that K controls how much smoothness you get out of your density estimate. So it will play an important role in the quality of the estimators that you get. If you are working on clustering problems, the number of components can typically be a parameter that is important on its own. For example, in our iris example, where we were trying to identify a species given some morphological characteristics of the flowers, one important question is, are we dealing with 2 species or are we dealing with 3? So do we have enough differences between versicolor and virginica to really tell that the 2 species are different, or the differences are not large enough and we can only treat them as a single one? So this question of how many components you have in the mixture can be an important one in clustering, and you may want to be able to answer that question in a statistically appropriate manner. So in terms of tools for doing model selection, and in the end selecting the number of components is a problem of model selection, one that is very popular and that can be used for mixture models is the Bayesian information criteria. Or BIC for short. BIC is going to be the primary tool that we're going to use to select the number of components in the context of the EM algorithm. And you may be familiar already with the BIC. The BIC for a model, and I'm going to index the model using the letter J, is defined as minus 2 times the logarithm of the likelihood of that model evaluated in the maximum likelihood estimator of the parameters for that model, plus the number of parameters that are present in the model multiplied by the logarithm of the number of data points. And you want to think about this guy as the number of effective independent parameters. And again, this is just your likelihood function and this is the MLE, the maximum likelihood estimator for the parameters in the model. Now, as you can see, the BIC is made up of 2 terms, and these 2 terms can be easily interpreted. So the term on the left is essentially a goodness of fit test. So remember that one way to think about what the likelihood does is tell you how well the model fits the data. So if this term here is high, then it's because the model fits the data well. And then the term on the right is a complexity term that just penalizes models that have high complexity. So if the model doesn't fit very well, then this number will be large. If the model has a lot of parameters, this number will be large. And so this expression just trades off complexity and goodness of fit. So in the end, you're going to tend to select models that have enough complexity to explain the data well, but not so much complexity that the additional parameters that you're adding just provides a marginal increase in this quantity up here. Now let's talk about the 2 terms in the BIC in the particular context of mixture models. The likelihood function in this case, we have already defined it before. This is the likelihood for the observed data not the complete data likelihood that we use for the EM algorithm to derive the Q function. This is just the observed data likelihood. And the observed data likelihood in this case, so my parameters for the mixture model is the vector of omegas and the parameters of the components of the mixture model. So these two things is what I called eta before. And of course, J, the index that identifies what model I'm working with, is really the number of components that I have in my mixture. So think about this as a vector that has length capital K, depending on how many components I have. And similarly, I have as many theta Ks as components I have in the mixture. And we have written this expression down before. This is just the product over the observations of the sum over the components of G sub K X sub I given theta. Okay. So this is the expression for the likelihood for the mixture model. We know that we can use the EM algorithm to get the MLEs for these parameters for any K that we choose. So it's easy to evaluate the first piece of the BIC for our model. Now, for the second piece, that was R sub J, that is the number of independent parameters in the model, we basically remember we have omega and we have the thetas. So omega has length capital K, but those parameters are not all independent. Remember that those parameters need to add up to 1 because they represent the weights in the model. So therefore, we have capital K plus, minus 1 independent parameters that come from this piece. And then it's going to depend on exactly what kernel you use. But for now, I'm going to call it the sum from K equal to 1 of capital K of the dimension of theta K. So each component is going to contribute a certain number of parameters to the mixture. And we basically need to think about the sum of all of those as the second component of this. So let's talk about a couple of specific examples just to make this a little bit clearer. So if you are talking about a location mixture of univariate Gaussians, for example, then this term that I'm calling the sum from K equals 1 to capital K of the dimension of theta K becomes, you have one standard deviation, one variance that is going to be the same because I'm only doing a location mixture. So you're going to have one parameter from there. And then each Gaussian kernel that you're including in the mixture give you capital K means that you need to include. So you have plus capital K. This is essentially sigma, and this is essentially mu1 up to mu capital K. On the other hand, if you are doing a location and scale mixture of p-variate Gaussians, then the same quantity sum from K equals 1 to capital K becomes, now you have one vector mu that has p entries for each one of the components. So you're going to have P times capital K terms that come from mu1 up to mu K, each one with dimension P. And then you're also going to have capital K variance covariance matrices Those variance covariance matrices are P by P, but you don't have P square independent terms in a variance covariance matrix, because remember that variance covariance matrices have to be positive, definite, in particular they need to be symmetric. So what you really have is P times P plus 1 divided by 2 elements that are independent. So exactly how you count the number of parameters that are associated with the kernel is going to depend on exactly which kernel you defined. And it's not really possible to give a very general formula. But these two examples should give you some guidance on how you need to pick those numbers for problems in which you're working with.